for the string, we're more interested in the average kinetic energy that one wavelength of the wave carries, not the average kinetic energy that one element of the wave has as it's going up and down. So the integral we have to do is in terms of dx over the wavelength of the wave. And so maybe you say, well, what happened? For that, we didn't need to worry about that. For that one, we wanted to know the average kinetic energy as a function of the whole path. So here, t kind of acts like your x. So when we do the integral, we do it in terms of t. Here, the wave is doing up and down a certain element of the wave, right? But I want to know at a certain time period, one wavelength of the wave, as it's traveling, how much energy is it packing, right? So when someone is there, how much energy is going to pass them in one wavelength? And then the next thing we're going to do is how much power is going to pass them. How much power is that wave carrying? Like a tsunami, right? So I don't care how much energy one element of the ocean is doing up and down, but I want to know how much one wavelength is carrying as it passes you. Let's see. So here's what happens. We do the average kinetic energy average kinetic energy over one wavelength. We can put it kind of like that notation. All right, so then we're going to have half m. So therefore what we can do is just assume t is 0. Because at any time interval, the kinetic energy of a wave over one wavelength should equal to the same thing. The time shouldn't matter because we're assuming energy is conserved. There's no dissipation here. If you want, maybe you can do an upper division level problem. You can say the wave is dissipating in energy. Then you can add e to the minus alpha x component, right? So what would that would describe a wave as it's traveling, it's dissipating, right? Or if you do e to the alpha x, that describes the wave that is increasing in size, which is what happens to a tsunami. Right? If the wave, when the wave is coming, you got the ocean floor gets shorter as the wave comes, right? So what happens to all that energy? It goes into the amplitude. So a tsunami is described by e to the alpha x, something like that, right? The amplitude gets bigger, and then here's your building, and you are taking a suntan. Right. Then it lifts you up with it, and here's a palm tree, then you can actually hug the palm tree. If you watch the movie Impossible, right, with Naomi Watts, that's how her family was saved. Her 2 children grabbed onto a palm tree in Indonesia, I think, or Thailand, and that's how they were saved. The wave lifted them up so high, and then the wave went by, and the children were saved by just hugging a palm tree, I think. So watch that movie, Impossible. Pretty powerful. Okay, so now we're doing a wave that's stationary in amplitude, right? So then we're going to do t is 0, the radians is 0. So we're just going to find the average energy of this wave. So then we're going to do a squared, omega squared, cosine squared, kx. Okay, now we introduce something in order to make this integrable. What's m? M is a certain element of the wave which has a mass dm, right? And then I want to integrate that over the full wavelength of the wave, right? So I introduce something known as the mass uniform, as the linear mass density of the wave. linear mass density. Then I can say dm is the mass of that is du dx is the mass density times that portion of the wave, right? So then the kinetic energy is going to be 1/2 mu dx. There you go. Now this is coming along. So this tells me the kinetic energy of one element of the wavelength of a wave at any time period. Because that element is traveling to the right. You see? And it's, of course, it's also going down, but we're not interested in the down motion. Right? We're interested in the kinetic energy to the right. So now, if I want to find the total kinetic energy, I add these up. Right? So this, we can call this dKe. Right? So the Ke total is going to be integral half mu dx a squared omega squared cosine squared kx from 0 to 1 wavelength. That's the total kinetic energy carried by one wave. Half a squared mu omega squared integral 0 to lambda cosine squared kx dx. So this one we can use the cosine squared rule again. 1 plus cosine 2kx over 2, right? So that square rule is very, very useful here. From 0 to lambda, then you put the lambda in there. This becomes a quarter, right? Then you put the lambda here. When you put 0, you get what? 0 here. 0. Oh no, I didn't integrate it. Sorry. I haven't integrated it yet. The integral, I still have to do the integral of this, right? The 2 comes out, makes it a quarter. The integral of 1 is x, and then the integral of cosine is sine 2kx over 2k. Now you go from 0 to 1 wavelength. Okay, now I believe when you put 0, this is going to give you 0. When you put the wavelength here, you're going to get lambda. When you put the wavelength here, you're going to get 0 also. Because you have 2k lambda, and k is 2 pi over lambda, so you're going to get sine of 4 pi again. So the only one that matters is just putting lambda in there. There you go. I believe that's the equation. This gives you the total kinetic energy carried by one wavelength of the wave at any interval of time. Okay? Carried by one wave. So quarter a squared w squared times lambda. What does mu represent? The mass thickness of the string, right? If you use a thicker string like a big rope, right, it's going to carry more weight. So it's interesting here to see that some of the quantities here are squares, whereas others are not. The kinetic energy of the wave depends on the amplitude of the wave squared. So if the amplitude of the wave is double, keeping everything else the same, it carries 4 times the kinetic energy. You see? That's why the tsunami is dangerous. Not only because its amplitude is large, but the kinetic energy that it comes with 4 times as much if you double. You see? It hits you with 4 times the amount of power and energy. The frequency of the wave also is squared, which means if it goes up and down quickly, and you double the frequency, it goes, the kinetic energy is quadrupled. The wavelength of the wave is not squared. So if you double the wavelength, you only double the kinetic energy, right? If you double the wavelength, so that means from here to here, the wave is more like this. You double the energy. But if the frequency is doubled, it's more dangerous, you see? So now if the kinetic energy total is that, what's going to be the total potential energy? We're going to argue by simple, we don't have to do the whole integral again, by simple symmetry, we're going to argue that it's the same. And then when you add them, you're going to get what? The total energy of the wave. So this is potential energy plus kinetic energy. Right? So basically, when you do quarter and quarter, it's a very similar thing that's what happened to the block and the spring. The quarter, the half, when you add them, you get a half. That's the total energy, but each one is a quarter, right? The last thing to do is to derive an equation for the power of the wave. The total power of the wave is what? The energy of one wavelength of the wave divided by the period of the motion, right? Because power is energy over time. So now you're going to have here half a squared mu omega squared lambda over the period. But what's lambda over period? Right? Velocity is lambda times frequency. Frequency is lambda 1 over period. So lambda over period is just the velocity of the wave. That makes sense too. If you double the amplitude, the power of the wave quadruples. Double the frequency, the power of the wave quadruples. Double the velocity, the power only doubles. Double the mass density, the power only doubles. Okay? The thing that's really hard is to, let's say, don't even look at these equations and then try to explain to a 5th, 6th grader without any of this math. Show them a traveling wave and describe to them what the amplitude of the wave, the velocity, the frequency. Now describe to them the dependence of the power of that wave on the amplitude, on the frequency, on the density of the wave, and the velocity. Now try to convince them that the power should be square function of the amplitude and square function of the frequency, but only a single power of the velocity and single power of the mass density without any of the math. Okay? One way you could do it is to show that the units match up. That if you square amplitude, you square frequency, you know, and everything, the units come out watts. But that's cheating. All right? Just to argue in terms of units is cheating. More conceptually, try to visualize. Why should the power of a wave quadruple if I increase the amplitude by 2? See, like a wave like this versus like that. What should it be quadruple? Can you explain? But if I double the velocity that it's traveling, power only doubles. If I double the frequency, how fast it's going up and down, the power also quadruples. Right? That's pretty tough. try to do it non-mathematically. See if you can think about that as you prepare for test 1 on Monday. Okay, so test 1 Monday, we start in the other room like around 10:15 so that we can have the full hour and 45 minutes. Okay, see you guys. Study hard.